Here we are, class 18, Pkt6, Monday, 10th of May. I've always said I'd rather have a Monday in May than a Friday in February. The end is near. February is a rough month. It seems like you got a long haul, man. But in May, that light at the end of the tunnel is shining brightly. So I can handle a Monday in May. There it is. We all say it together, really. 1, 2, 3, 10. 10 more days of teaching. Now, I think there's 14 school days, but like one of those is out on the West Lawn playing cornhole and volleyball and other stuff. One is taking the test 5-6B. 2 are finals. So that leaves us with 10 more times. No, I guess in our case, we'd say 10 more Zooms. And that finishes us for May, at least. Last week, we had the beginning of May. Not a lot going on. This week, a few more things going on. We'll meet table 4 either, which means I'd meet one of you either tomorrow or Thursday. We'll do one or the other. I'm working on your test 6A. I'm assuming everybody's taking it. In class, I can count them. I know that everyone but one is taking it. And I don't know if he ever will, but here, virtual, if you go, oh my gosh, first time I've heard of that. I don't looking at the screen here. I think all of you have taken it. So if you're watching this recording and you haven't taken it, you better get with me real fast, because Wednesday, it becomes an absolute 0. You're already losing points, but Wednesday you go to 0. And this is not a beer. It is Topo Chico, okay? It's just water, little grapefruit. All right, so Wednesday, you'll get that back. And for you all, I'll post the scores. Oh, yeah, I'll post the scores Tuesday night. You all, I'm doing it different this time. I've taken all that you turned in. If you've emailed it to me, even if you did it on Canvas, and I've taken it and I put it on my iPad, so I can now annotate your work. First time I've been able to do that. And then I guess I'm going to just have to, but maybe I can reply or somehow I have to email it to you or something. I'm just seeing if this works okay. So I'll probably email your test back to you with, score, but not just a score and not just a description of, oh, number 1, you got a 5 out of 7, but circling what you made mistakes on. So for all those that emailed it to me, you should get an email back from me with your test. Okay. It's not something I want to do very often because it takes a lot of work, but I want to see how that works. So anyway, Wednesday, then you'll be able to redo your test. If you gave it to me on my front porch, I suppose I could take a picture and send it back to you or something. But if you send it in, I'll fix it up and send it back. So Wednesday, and then Friday it's due. Turn back in, submitted back for you all. Submit would be fine. The blue work on Canvas. Yeah. Now, Thursday night, this does involve you. Thursday night, we have Flash Off, and we're done with Flashback Fridays now. Flash Off. That, if you all win, you will be, they're going to hate you guys. So it's your chance to be a spoiler. It'll be virtual plus all the other classes this Thursday, 7 p.m. We'll cut it off at 7:45 no matter what. And at that point, we'll see who's ahead. Now, not every song is worth 1. Some are worth 2, some are worth 3, some are worth 4 points. And we'll do it all by chat like we do it. Okay. You have the advantage because they've never done it by chat. And you'll put down V and then your name. Well, no, you'll put down V and then I'll know who it is because your name is there. But you'll put down V and then you'll put down the title. Or maybe the title V, whatever. So that they know it's virtual. I'll know it's virtual. If you win, then Friday, the 14th, I'll announce it and I'll do something for you guys. For them, I'm doing like a pizza party for third hour, first, second hour, getting donuts and bagels and juices and milk and things like that. This is just something out of my pocket so it can't be too much, but I thought I'd do something for you guys. So we'll see. Well, let's wait and see if you win. If you win, you'll get whatever money I was going to spend on them, I'll spend on you somehow. Next week, the PDF of the 150-point test 6B, take-home test 6B is available Sunday night. I'll hand it out to them on Monday, but you'll see it Sunday night. That that's the beginning of the end. You know that Pkt6 is almost done. When you get that take-home test, you know at the beginning of the end. So that's Monday. We'll go through all that. We'll do a Zoom help session for that 9 to 10 on Thursday night. And then on Friday, I'm supposed to tell you everything I know about sex. That'll last about 2 minutes. And then in class, we're going to go out in the West Lawn. And we'll have like a physics day, but a kind of a fun day. We'll do a tug of war. We'll put that meter in the middle of it. We'll have some food. We'll do a spring dance. I'll show them all the spring dance, or they'll just do the spring dance. I'll film that. That's always fun. We'll do some bocce ball, volleyball. We'll take a class picture of each class. We'll do a play some cornhole tournament. And then here's where you guys come in. I want you all to come up to the West Lawn, if you can, at noon on Friday, not this Friday, but the 21st. It's our last Friday of school. And we're going to get a class picture. And all my students, now normally, these are my alumni because it's an alumni picnic, but this year we're not supposed to invite alumni. So we take about 6 of these a year, 6 of these in that day because they come in waves. All these people in here are alumni. There's Isaac, John. You may recognize some of these people. Now a lot of these are 40 years old. Alexi's finishing up his degree in astrophysics. Sarah's doing amazing things now. So all these people are out there, robotics, doing all kinds of stuff out there in the world. So it won't be them, but it'll be you all. But if I can get a picture of 75 students all together for one time, that'll make me very happy. So we're going to get our class picture, and then we're going to have like hot dog, chili cheese dogs. We'll have chips and Coke. Now I may have to charge like $2, but trust me, it'll be cheap because I'm once again, it's out of my pocket. I don't have a canteen anymore. So just trying to recoup my costs from my bill. But it'll be a cheap lunch, and if it's a beautiful day like today, be great. So that's a coming, not this Friday, but the next Friday. And then we have finals week. These read this pretty obvious for you all. I know like Rose got to come early because she's got to be somewhere. So she's going to come and take it on the 25th, I think, or the 25th, I think, with the rest of the kids. If you want to do that and not do it online, that's fine. You can always come in 25th, 26th, or 27th, really, in my opinion, and just come into class. Or you can sit back in the prep room. There's fans on. It's very, very safe back there. or I will send it to you. And all the instructions are here. Okay. Then the June project starts June 3rd, the Physics June project. More about that here in a minute. So that's the calendar for the remaining 3 weeks of school. I have a new help sheet, side 16. There is there's one here on the, this is from an old book I was working on many years ago, and I've kind of just taken it and pulled pieces out of it. So this is example 28 from that book, and it shows force of thrust on a rocket. It shows the equations, the free body diagram, and then over here is one of the little boat being towed by a big boat. And then I had my head to tail to my free body diagram, but I like Brandon's better. And so I took mine out, put Brandon's in, and this is Brandon from the last test. I liked his use of color, the little red check marks on me, checking off stuff I'm looking for. And I thought he did a phenomenal job. So I thought, well, why not honor him? And Laurie did a great job. I just happened to have, mine was kind of sloppy. And so I thought his looked better. And then the last bit on there is buoyancy. The whole thing's about buoyancy. These are things we've talked about, but it's all there on side 16. Side 17 comes this week. That'll have like Newton's third law and boxes on boxes, things like that. That I may have to, that one, we'll see. And what else we got? Oh, so speaking of that, I said that this flyer comes out today. It will, I send out, our website goes live. We were supposed to go live last night, and then there was a few more things, a few more kinks we have to fix today, and then it'll go live tonight. And so this will be available. I'll send this out to everybody, to like 5,000 emails. I'll send this out, and this is for our kickoff of our classes in June. And so we're offering, now in the fall, we're going to offer, I think, 6 classes, but in June, we're offering, these are our inaugural classes here. There's Dr. Fournette, and he'll do a really good series, I think. It sounds like he's been talking all about it. He's all excited. And it's why are there so many kinds of animals, linking ecology and evolution. So the only prerequisite for that is you have to have had high school biology. Okay, that helps. He'll probably take you if you hadn't, but all of you have. And then I'll do mine on from gravity to the ultimate fighting tool. We'll take it from, so it's kind of how the whole thing fits together in 12 sessions. And you could walk in off the street and take it, but it would be a lot easier because you all know all the lingo, right? And so I'm assuming it'll be mostly my students, but I'll certainly accept adults or other kids from other places. And then Mike's world known on his guitar. He's aficionado on he's a member of a couple of groups, and he writes his own music. He writes he's a composer, but Mike is a great teacher. The kids that have had him as a guitar teacher rave about him because he won't let it go. If the thing takes an hour, but if it takes 2 hours, he'll stay 2 hours until you get it right. So he'll work with you on your, all that. So that starts, his is once a week. Dr. Fournette and ours are 3 times a week. His goes all the way to August. Ours will be done at the end of June. So you can take all 3 classes. You could take one or none. But anyway, so if you go to askmelearning.org right now, nothing will happen. It'll go to an old site. We're going to unveil it later tonight, certainly by tomorrow. Okay. Finally, I know some of you want to go into aviation. You want to go into aerospace, and I'm not a big fan of tattoos. I think they're great. Nothing against them. But I'm, this art, I just love this art. This is a great tattoo. Okay. Now, I didn't go around and do any stargazing because now what I'm going to check up on you is 6'4" and maybe 6'6". We'll see. But nothing today. We did our joke Monday, Stiffly Stifferson. I'll probably get fired over that one. And then I wanted them, they've already made it. If you've been to our Facebook group, you've seen they've already made the memes now. And that's that these two, remember that meme that's an office meme, and Pam is saying, well, corporate asked us to see the difference between these two, and there is no difference, and that's what I was trying to get at here. That's head to tail method with the resultant, and that's free body diagram with the resultant off to the side, because you don't put resultants in free body diagrams. And the point is, these are the same thing. And I only say this because on the test that I'm grading that problem right now. And I know that there's a number of students who, when you do head to tail, they did it one way. And then when they did free body diagrams, like they made up new vectors. Like, where'd you get that guy at? So they don't get the connection between the two. But that only happened on about 6 or 7 kids. But that's 6 or 7 too many. You should not. I told Jamie, my wife, that there's been a lot of bad things this year, just disappointments, not disappointing you guys. I'm talking about just the way life is. But this is one thing, one spot, one bright spot was you all, and I've graded yours, you all understood this better than any other year I've ever taught physics. The head to tail to the free body diagram. Now, I've tried something different, some things differently. This, I think it worked. So that is a bright spot. Okay, on Friday, I was having to wave my arms because I couldn't get the screen to work, but there's your elevator equation. And so we talked about that. If that Friday, didn't quite work for you, me talking about the elevator, here's a 4-minute lecture, and this is on, I'll put it again in the comments for today, but this was in the comments for Friday, and it's not me, it's another professor talking about elevators, and elevator equation. It's a good 4-minute talk. He does a good job. He's chalk and talk, but he's very thorough, very simple version. So this was us Thursday, Friday. We'll come back to this in a minute. On Friday, we talked about the aliens pranking you if you were, say, out floating a box with no windows, floating in outer space, in interstellar space, and you fell asleep. Then the aliens come along while you're asleep, and they hook up some cables to your box, and then they pull you with a thrust. They thrust their engines, so they're accelerating, and they accelerate you at 9.81 meters per second squared. You are going to then be thrown down to the floor, and you're going to think that you're back on Earth, and you fling open the door, and then you're exposed to the vastness of interstellar space and the vacuum, and of course it's curtains for you, but they get a laugh out of it. So the idea was you can fool gravity. And so I don't know if I showed this to you or if I just had to try, and I think I probably held it up to the camera or something. But here is the called the equivalence principle. Those little 3 lines mean equivalent to, not equal to. Equal to is numerical, but equivalent to is conceptual, showing that gravity has the same effect on something as just acceleration is. So in gravity's case, like I weigh, say I weigh 190 pounds on Earth, because my mass is being pulled down to the Earth by the Earth's mass. And that, by the way, is Newton's universal law of gravitation. That's the first thing we'll start to study in June is this, because it is a universal law, right? It is it's one of the top 5 relationships ever written. So and it basically explains or dictates astrophysics. It just dictates how big, massive planets and moons act with each other. That's the attraction. So that's what that's what Newton would say. Oh, by the way, okay, well, let me finish this. So the point that Einstein's making is that in gravity's case, I can get in that same box, have my engines fire and thrust m dot VE and force my box to accelerate upwards. And then I would still feel like I weigh, in this case, 150 pounds. It says it'd be my apparent weight, all right, is 150 pounds. So either way, you get the same thing, whether you're standing by a massive object or whether you're just being accelerated. By the way, flat earthers, because they get criticized, asking them to explain gravity. I've heard this explanation from a flat earther. I used to argue with, I don't know, I don't anymore, but a couple years ago. So a flat earther explained, I said, well, if you, how do you determine weight if, you know, if you don't have that solid sphere underneath you, you have this, instead you have a flat, plane. There's not enough mass between you. So their explanation was that, oh, the earth is, this flat earth is being accelerated upwards, and you feel like you weigh, like me, 190 pounds, but it's because you're being forced up on this flat earth at accelerating at 9.81 meters per second squared. Well, on the surface you go, oh, okay, well, that's legit. But one problem, you're accelerating, right? So you have to keep accelerating. Well, there's a limit to how fast you can go. Speed of light, which you would get to the speed of light. Somebody could figure it out real quick. Delta X equals V times T. I don't know, A times T. V final equals A times T, right? If I plug in, this is flat earth talk. If I plug in V final equals A times T, I'm sure they'll agree with that. Then A, you plug in 9.81 meters per second squared. And for V final, you put in speed of light. Let's just say 3 times 10 to the 8th meters per second. And then the question is, how long will it take you to get from 0 to that? And not that long. I don't think. You divide that. Yeah, I don't know. It's a few. It takes a little while. But if I let's say divide by 10, that's still 3 times 10 to the 7th. Divide to seconds. So that's, in other words, you're saying that's how long then we have before we're moving at the speed of light. And you can divide that by 3,600 and give me hours. You're not going to be, how long is that? How many days, how many weeks is that? The point is, don't even care. The point is that flat Earth's, quote, pseudoscience falls apart after 5 minutes of inspection. So then we have all these. Oh, here's one. It's kind of nice. This guy on the left side, he's dropping a ball. Okay, drop a ball, it falls to the earth, gravity. On the right side, he's not dropping he lets the ball go, and it would normally float if he's weightless, except if the ship is moving up at 9.81, it would fall. So it would apparently, from his point of view, still be like on Earth. Okay. All right. Now, the last thing I want to talk about that one is this. You'll need to draw this on your paper. So I'll give you a minute. Draw these two boxes and draw this little guy chilling here in a corner. And then this up here, this is a laser. I'll make it a green laser. So this is a laser. Okay, like a laser pin. All right. So draw these two boxes. first scenario, you are laying there and then you see this laser up there, and then somebody flips a switch and the laser comes on. And of course, what's a laser going to do? It's going to point straight at, and so here goes the laser. Zap. And it hits the wall right there, as you'd expect. Okay. Now, along underneath you, somebody brings in something extremely heavy. Right here. Really heavy. I mean, like the heaviest thing you can think of. For instance, your mama. So somebody brings in, sorry, it's close to Mother's Day. Somebody brings in your mama and puts her underneath you so you, unbeknownst to you. Okay. So you have this incredibly heavy object. Now, and dense. Now, when you turn that laser on, because as Einstein showed, space-time is curved, the laser goes along like this, and it curves into the direction of that mass. Now, this is weird, I agree, but it was proven in 1919 by Sir Arthur Eddington. Einstein had written out and had presented the paper on general relativity in 1916. And while everyone agreed that sounded very interesting, math-wise, no one believed it, that it really worked, that light really was bent, or things did, or large objects did bend this space-time as Einstein was talking about. So Sir Arthur Eddington in 1919, there was a few expeditions, but he led off on an expedition, him and a whole crew, and their job was to film or to photograph a eclipse, because here's the thinking: there's stars like lined up behind our sun. We can't see them in the daytime because our sun is too bright. So if an eclipse eclipses the sun, then everything becomes dark. You can all of a sudden see the stars, and then could film it, and he could see with the apparent position of the star. We know what the star really is in its apparent position, and show that the star's light has actually bent around the sun. Einstein predicted it would bend something like 1.2 degrees or something. And then when Eddington brought back the photographic plates, they did spend a long time on it. And sure enough, it bent. Light from this star did bend the exact amount to the nearest 2 or 3 digits that Einstein had predicted. Einstein becomes an international celebrity overnight as his paper is being presented. But really, not many people knew about Einstein except within his physics circles until then. Then he became a, star. All right, so that's cool. Now let's take the same scenario, little pink rooms, and we take that laser, and we're sitting there. We turn it on. It hits the wall as it's supposed to, a straight line. Now we don't put your mama underneath it. We instead accelerate the whole elevator. We wait until the laser started, flipped on. We accelerate the whole thing at, let's say, I don't know, 0.5 C. Lowercase c is the speed of light. So let's say we're doing half. So instead of writing out 3 × 10⁸ meters per second every time, I just say c, lowercase c. So let's say it's accelerating at 0.5 c meters per second squared. All right. Now, follow me along here. that light leaves that laser, pop, 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 and once it leaves that laser, remember, now the ship, the box that it's in, is accelerating upwards. So where will this laser hit the wall? On the other side. It leaves the laser pin. At that instant, the box, this is a Gedonks, by the way, right? This is a thought experiment. This is a pondering. You're pondering, all right? It leaves that laser. The elevator or box that it's in now is accelerated upward incredibly fast, half the speed of light per second. Where will this laser hit the other wall? Will it hit like it did?
My first guess would be to like it would hit up above it, maybe.
If the elevator was if the box was going down, but the box is accelerating up. Okay, I got this slide from Caltech. I think it was Caltech or Stanford, somewhere in California. This is from Sean Carroll, a physics professor. That's his slide on that. So here's the light. It takes off. The light continues to go straight. Okay, there's no huge gravitational force around it. So the light continues to go straight, but because the box is accelerating upward, by the time the light gets to the other side, it's hitting below. And so the light then bends. The light then bends. Speaking of thrust, the light then apparently bends. It's apparent bending. Okay. It didn't, because the light really looked, from the light's point of view, it looked like this. It just kept going straight. But from your point of view, inside that pink box, you swear that light bent, but it didn't. So once again, be it a huge gravitational attractor or acceleration, the effects are the same. Now, does that make sense?
Would the heavy object like make you heavier too?
Yes.
Okay.
This is like a donks. So like a donks is, a thought experiment. You can kind of suspend some things, because someone go, wait a minute, aren't you going to get smashed if there's a heavy object? Wouldn't you know? Well, yes. And if you were here, wouldn't you be thrown to the floor so badly that no way you're going to be looking at it later? No, this is like a donks, man. You're pondering, but you are correct. I saw something on, I don't know what it was, some group I was on, and it had like IQs, and it said they were naming off IQs. Einstein was 160, Hawking was around 160, about the same. They had Tesla. They thought he was around 180. But the thing is, so they were saying, well, Tesla's got a higher IQ than Einstein, and Einstein fully agreed with that. That Tesla was the genius. But the thing that Einstein had that Tesla didn't, and Tesla had a great imagination, don't get me wrong. I mean, he was anticipating Wi-Fi way before anybody else. He was anticipating remote controlled or autonomous cars way back when cars were first starting. Anyway, but I think Einstein had a better imagination when it comes to these kind of thought experiments. that he was the master of that. He was always saying, well, what if, to get himself to understand it, he would make up these scenarios. That's why he loved elevators, because that's a way to change, to make your inertial frame of reference and move you left, move you right, move you up, down. So weird things happen, and then explain why. But this is how this kind of thinking that he's doing led to the general theory of relativity. So that's why I suggest that every once in a while you take this thing and you put it down. I mean, you're not going to. It's good for communication. I'm not saying I don't look at my phone, but I don't. I mean, I'd learn basic stuff, but in order to ponder the world, you can't do it by looking at a phone. It can maybe get you started thinking, and then depending on what you're looking at. But I'll I rode my bike the other day. I was just thinking about wind. I spent, I think, an hour thinking about wind and the air molecules and the paths of the molecules and why this leaf goes this way. Why does it flutter? What's happening to the physics there? Because wind is, that's where tornadoes are, I mean, it's not like it's a little deal. What's causing all these pressure differences with the jet stream? What's going on the North Pole? Just pondering it in my head for over and over, and I had to pull over a couple of times, just sit down and think, trying to put this together. And no phone involved. I mean, phone would have messed me up. Oh, I'll go look on Wikipedia. What? No. Let's sit and think. So that's what I'm trying to encourage you to do, is you can go sit in your room and start looking at paint and go, well, why is that paint red? Why is that paint white? What's the difference? How are my eyes seeing that different? What's the frequencies? Oh, well, red's a different frequency than white. So I'm given different cones in my eyes. I mean, so what is white? All that kind of stuff. It's crazy. Light. What's light? I was thinking the other day, what is light? I'm laying in the backyard in a hammock. It was the daytime and I'm surrounded by light. And I think, well, what? And I think what got me thinking was photons don't experience time and they don't experience distance. So, but yet we say, well, the light from the sun takes 8.5 minutes to get to the earth, but that makes us think that photon is traveling, but it's not, because the photon's not experiencing space or time because it can't, because it moves at the speed of light. If you move at the speed of light, you don't experience time. You don't experience space. So I'm sitting there thinking, what's in this grapefruit? Okay. I'm sitting there thinking, what? And so I decided to say, okay, in the core of the sun, what starts the whole thing, right? Two hydrogen atoms get slammed into each other. And one of the products of that, and then eventually deuterium gets involved and then helium. But one of the products of that is a gamma ray. A gamma ray is like this waste energy, this excess energy that gets shot off as a gamma ray in the core of the sun. But yet gamma rays kill us. But it takes 1 million years for that gamma, on average, for that gamma ray to be deconstructively interfered with by the time it gets to the surface of the sun, and then it takes 8.5 minutes to get from the sun to us. At this point, we get Roy G. Biv, we get infrared, we get ultraviolet. So you get all these frequencies that we can use, but we've evolved to be able to handle that. Anyway, so this is my example of, and I did all that without a phone. I mean, just thinking, and that you end up, it's like drinking coffee, because you become revitalized. And even if you don't understand it all, it's just the thinking is really cool. All right. So sorry, get off on that subject. The homework is 6.7, 1, 2, 3, 4. And those are false statements, and you're supposed to make them correct. Let's do 5 as an example. 5 says the force due to gravity is the same on all objects near the surface of the earth. That sounds true. Why is it false?
Is it because we different masses? Or yeah,
Boom,
masses.
no, boom, boom. That you nailed it. So it's not the force that's the same. Like the force on me, I'm 200 pounds. The force on Sophia is probably 110 or something. So it's the same, but what is the same? Like if you drop this,
Acceleration.
yes. So if you drop this both off the stadium, even though her force is different than my force, we're going to hit at the same time, and it's because of inertia versus attraction. But if I could change one word to make this work, if I change force to acceleration, then it's correct. So it says here, give complete sentences. Don't worry about that. Just fix it. Sometimes one thing will fix it. Sometimes it takes 3 things to fix it. So somehow rewrite it, mark something out, change a phrase. That's what you're supposed to do on 1 through 4. Okay. I'm going around tomorrow and checking stamps on that. Now, the last thing, this is really the reason why we're here today, is to work statics. We're supposed to work this problem right here. Number 5, back on 6.6. That's why we're here. And I sat there and talked forever. So there's 2 ways to do this problem. One is the engineering. Engineers just plod along. God love them. They will eventually get the daggone thing figured out, but they will do it half the time in the most arcane, slow way possible. So what an engineer will do is they'll look at this and go, okay, I'm gonna make an XY axis, and this is called, by the way, a Truss problem, and it falls under statics. You'll take a course at college called statics, a whole semester, where you study things that don't move. So in statics, summation of forces always equals 0. In fact, velocity equals 0. Anyway, here's an example. So then they'll take this and they'll go, okay, here's my X, here's my Y. And then they'll divide this. They'll turn all these into vectors and say, okay, there's, let's go red. There's one vector, my T2. There's a vector, my T1. And then there's a vector, my T3. Now, T3 they gave you as 200 newtons. Then they'll take this, they'll make, okay, every vector at an angle is the right triangle, blah, blah, blah. And by the way, I hope you're not writing this down. And then they'll color that in, they'll color that in. Okay, then they'll find the X on this one using sines and cosines and Y's, and they'll take all the summation of force in the X equals 0. All the summation of force in the Y equals 0. They'll get 2 equations, 2 unknowns. It takes forever. All right, I'm going to show you a fast way of doing these particular kinds of Truss problems. It'll speed you up. You'll blow right by all the engineers when you get to college. Okay, here's what you do. I got 5 minutes. So you got 5 minutes left on the test. Here we go. Check it out. I'm going to go ahead and I'm going to extend. I'll extend this line back. And by the way, the lengths, the physical length doesn't mean anything. I can take a rope and just barely hold it tight, right? Put like 10 newtons on it and barely hold it tight. Or I can take a real short rope and hold it with 500 newtons of tension. The length of the rope means nothing. All right, so I extend this guy back. I'm going to extend this force back along the line of action. I extend this one down. I just make it longer. Bum, 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 bum. This is my favorite shortcut. And then, okay, I'll make it a different color. Make this guy red. And then this T1, I'm going to take my ruler. You can't do this freehand. Take a ruler and then come down here. I'll make it so I have a decent sized triangle. I'll make that green. And there's my T1. So T1, I'm redrawing. It was up there. I'm putting it down here. And we know that's pulled up. There's T1. T2 is the blue one. That's in that direction, T2. And then T3 is down. That's 200 newtons. It told us that. That's the weight of that light. So I have a new, and by the way, if I take these three vectors and I add them up, I get 0. Isn't that what statics means? So there is no resultant. So now I'm going to take this. How much time I got? 3 minutes. Okay. I'm going to take this and I'll color in my triangle. Oh, it's a good shortcut. Color in my triangle. And then I know that one side is 200. It's not a right triangle. It kind of looks like one, but it's not. Okay. I'm up against a wall here. Okay. So this guy, let's go to daggone it. Hold on. Don't leave me. Okay, here we go. This, all right. Yeah. So let me draw a couple of quick lines here. And right. So now let's do some geometry. If that's 40, what is this angle right here? Pepper, come on, hang on just a second. If that's 40, what is this angle? What must this be? Geometry. 40 and 40 here. Thank you. Corresponding, right? And so, and so
I said it first.
okay. And so this is 40. If that's 40, what is this angle?
50.
50. Pepper, daggone it. Okay, I'm almost done. If that's 30, that's 30, alternate interior angles. And then isn't that 30? Therefore, what is that angle? And by the way, this is the way you do it every time. What's that angle?
60.
60. Therefore, what is this angle? Oh, not 90. Yeah, it's not 90, right? It must be 70 because they have to add up to 180. Pepper, pepper, pepper. All right, so now I have the three angles and I have a side. Anybody know the law I use now? Not law of cosines. It's the law of sines. So sine of A over A equals sine of B over B equals sine of C over C. A, if you call this, so let's throw it in there. So we have sine of 70. Pepper, I'm going to get you in a second. Sine of 70 over 200. She's stuck in a corner over there. Equals sine of 60 over T2 equals sine of 50 over T1. And now all I got to do is cross multiply. Trust me, I went slow on that, but you can do this in I did it in 5 or 6 minutes. You can do it in about 3 minutes. And it's a way of solving these Truss problems. Okay. Pepper's going into, it's just going to get worse. Pepper's going into absolute freak out mode. Okay. So that's it. I will let you go. And tomorrow we'll keep on going here. Work on that homework. Questions? You guys are free to go unless you have a question or you want to hear Pepper bark. I'm coming, Pepper. I'm coming.